Any questions from last time? Okay, so the last thing we talked about were these R module homomorphisms. These are just linear transformations for modules, right? The scalars you pull out are from the ring. This is basically what you need for a linear transformation. See, of course, P is function from R module A to R module B. And this is what an R module do. No example. A Z module homomorphism is the same as a billion groups. These are exactly the same. So that's another kind of connection that I like to see. Right. Let me give you a couple of examples here. I think sometimes get a little confused. There is a difference, of course, between this and a ring homomorphism. Example. Let's let N and T to Z be the following functions. So this is basically, you've got a fixed N and you scale everything by N. It is easy to verify that this is if X and Y are integers and N is also an integer, then this is equal to N X plus M Y, which is N X plus M M Y, which is Fn X plus M Fn Y. So this is an R module homomorphism for sure. But Fn is not a ring homomorphism unless what? What condition on N makes this like a ring homomorphism? One, right, and then it's the identity. But see, here's the problem, because Fn of xy is not equal to nx times ny, it's just n times xy, and you've got a problem there. One could also argue unless n equals 0 as well, but that would be the 0 ring homomorphism, and some people demand that ring homomorphisms take the identity. The identity, you might say 0 as well, but that's a little bit more controversial, depending on whether you want your target to have an identity or not. Here's another example. This is here's another example, and this shows kind of a theme of some of these R homomorphisms. But well, let's let R be a. You need to bring one. You can generalize this, but I'm a lazy man. Define F from Rx to Rx via F of the polynomial P of X is x cubed x. So basically what you do is you take your input and just multiply it by 6 polynomial x. There's nothing special about x. I could have picked any number of other polynomials. This is a R module homomorphism, but not a ring. Okay. So let me say that this is. I will sometimes add descriptors to my R module homomorphisms. I might, for example, say an R module monomorphism means 1, an R module epimorphism means onto, an R module isomorphism means it's an isomorphism, like that. Just like you're used to. That's one of the cool things about algebra. You see these recurring things, right? Group homomorphisms, ring homomorphisms, R module homomorphisms. We discussed this one a little bit. Let me write this down so that notes here. Make let M and N be R modules. Then home R M N. We define this to be the set of R module homomorphisms it's a set of all R module homomorphisms from M to N. And this is I mentioned this last time, it's in the group. Let me. And here's the way we define the addition in our abelian group. If F and G are both homomorphisms from M to N, then I define the new homomorphism F plus G of N. Its output is just F of N plus N. So it's just pointwise addition of the function. It's easy to check that is again an R module homomorphism. If R is the U-bit, then all R M N is an R module. And again, you be careful about it. So what do I mean by the function R times F? Where R is an element of the ring and F is a homomorphism. It's just R times F. Okay. Let me just quickly say that if then F and G are at home R in M. Then F, the new function F plus G operating on X plus Y is by definition, which is F of X plus F of Y plus G of X plus G of Y, because both of those little animals are module homomorphisms. which is right. Grouping these together, this is f plus g of x plus these together f plus g of y. So I've shown that this is closed under addition. The identity of this is just a function that takes everything to 0 over an n. It's easy to check that the function minus f that takes minus f takes n to minus f of n. That's the additive identity or the additive inverse of f. And you can verify in the commutative case that this is a module as well. Okay. Definition. So we know what homomorphisms are, and as you might suspect, there's going to be a connection with homomorphisms and submodules, which I haven't formally defined, but we'll do so now. Definition. And I'm going to do this in terms of left and right, although I will quickly relax and focus on commutative rings. Let M be a left R module, and N, right? Because remember, first and foremost, M is an abelian group, so I'm going to pick some subgroup N. Well, so any subgroup of M is a candidate for being what I might call a submodule, right? I mean, we know what sub stuff means, right? It means like a little baby inside the parent here. Well, any baby that M could have, any submodule, has to be an abelian group. Can it be any abelian group? What else do we need for this to be a submodule? N is a submodule of M if Rn is contained in N for all. So just like ideals, this has to act like a vacuum cleaner, right? So in other words, the scalar multiplication that comes from the module M has to take N into N, right? And again, this is sort of like, when you first did group theory, this is sort of like a normality condition. You can't just have any old subgroup. It's got to be stabilized as a set by multiplication by any scalar. You got to stay inside there to really call it an R submodule. Okay, any questions? I'm going to give you this proposition here, which I hope this is familiar, that you've seen this in other contexts. The ring and M a left and unitary. Remember, I always assume that R has an identity, and 1 times M is M for every M and M, unless I tell you otherwise. Then N is contained, the N contained in M, a subset, is a left R submodule. You know, if and only N is not empty, and also you might have seen something like this when you did group theory. It's called this like subgroup criterion or something like this. Suppose N is a say let's first assume that. Then 0 is in N. So N is not empty, right? Because it's a submodule, it's got to at least have 0 in it. So it can't be empty. And if X, Y are in N and R is in R, then RY is in N. Because the definition of left submodule, R times anything in N is still an N. So RY has to be an N. So X gets RY is an N. Let's go the other way. Okay. So now what do we know? We know N is a non-empty subset, and we know it's got this property, right? We need to show it's a submodule. Right. So I'm gonna bootstrap this. Put N be an N, right? But notice that N plus -1 times N is N. So this is a step that I could have kind of skipped over this step, but I think that's all I can do. So, and this gives kind of a theme of what we're going to do. Now, if N and M are in N, then N plus -1 times M, which equals an N minus M, is N. So N and M is a subgroup. Because given any two elements, X, Y inverse, in this case, N minus M is in there. So that's the subgroup criteria. So I've got that laid. And so the last thing I need is to show this condition here that Rn is an N. But again, finally, if N is an N, then and R is an R. I guess that was convenient to do this. I already know from my first step that 0 is in there, so 0 plus Rn is in there. So when I multiply R times N, it's still an N, so R N. There you go. Okay. So, for example, here's kind of an interesting concept, right? Which isn't really surprising, but it's probably worth saying something about. Suppose that I'm in the special case where R is Z, right? So now I'm with Z is model. Any subgroup is now a Z model because it's sort of automatic there, right? Okay. Here's another sweeping example. I like this one here. Example. It's 111. Okay, so I'm going to start here. Suppose that I have a homomorphism, an R module homomorphism. There's all kinds of cool submodules creeping and crawling around. Suppose I have an R module homomorphism F from A to B. Then the kernel of F, which is all the crap in A, such that F of A is 0, a submodule. I really should say R submodule, but here the ring is constant and unambiguous. Sometimes I will be lazy that way. The kernel of F is a submodule of A. The image of F the image, so this is just, F may not cover all of B, but whatever it does cover is actually a submodule of B. And finally, here's another one that's worth noting. It's actually a generalization here. If C B is a submodule, then parts of C. And what is this? Well, this is all the garbage in A, such that F of A to C is a submodule. Um, Tell me what's the relationship? I did say that F inverse C is a generalization. Generalization of what? Oh, it's F inverse of zero submodule, right? So if I really want to sketch for you why this is true. I really don't have to worry about this kernel crap, right? Because if I do this here, I've done it. So let's look at the image first. Uh, let's do image of F. Um, let X and Y be in image of F. So, and R and R. Let me point out, I'll be lazy enough to write this down, but let me point out that the image of F is not empty, because in particular 0 is in the image of F, right? It's not empty. So suppose X and Y are in the image of F, R is an R. So there exists A1 and A2 and A such that F of A1 equals X and F of A2 equals Y. Since A is also R module, then A1 plus RA2 is an A. And if you look at F of A1 plus RA2, this is F of A1 plus R F of A2, which is, what the heck is it? It's X plus RY, which is in image of F. So I've shown it's a submodule. Because if I take any XY here and R, then X plus RY is still the image. Everybody cool with that? Let's look at F inverse C. And X, Y in F inverse of C. And R almost be the same kind of thing here. Note that by definition, F of X, F of Y are in C, and so is F of X plus R F of Y. Hence, using the fact this is an R homomorphism, so X plus RY is in F inverse C. And again, I didn't make a remark, which I should have, that F inverse C is not empty, but it's certainly not, because 0 is an F inverse. Okay. Here's another example. And this is, well, this is really more instructive than the get your garden variety example. For this one, let's suppose that I have my favorite R module A. Let A be an R module. And X and A sub set. any subset, no structure, just some collection of crap. In fact, it could even be empty. Then let me then funny brackets X, the R submodule of A spanned by X is I'm going to define this to be, this is the smallest submodule of A. So I just pick this goopy set, right? You get this big module, and I just pick out whatever I want. Here's my set X. I want the smallest submodule of A, the minimal submodule of X. And how would I define this? We're a very definition I like that. In fact, this definition is very important. It's kind of a workaday thing, right? Where, in fact, when you're doing stuff, you're gonna look at linear combinations of stuff in X, and that's what you should do. But what if X is empty? What does that mean, for example? So let me give you something that's like sort of mathematically looks fancy, but maybe not as good in practice, and then we'll talk about how to do it in practice. This is the intersection of all submodules and contain A. So just take the collection of all submodules that happen to contain X and intersect them all. Notice that this intersection will necessarily contain X. And it's sort of clear, isn't it, that this will be sort of minimal because you're intersecting all of them. So that's like, I can write that up on the board and come home and feel very fancy about it. So look at that. But let's talk about getting more practical, because maybe you want to actually do some computations, or there's something about this module you need to know. Well, here among some cases here. Oh, right. So this actually answers that question at first. So from this perspective, what happens if, well, let me point out that, for example, if X is all of A, so if I pick this all out, then of course this will be A, right? What if X is empty? And you intersect every submodule, including zero. Like zero is contained in every. So actually, the module generated by the empty set should be the zero instance, right? For example, if here's some important cases to consider. If X can be written as the union of BI, where each BI is R submodule A, so this admittedly is kind of a special case, but it's important here. Then the model generated by X is the sum of the BIs. And we write, in this case, X is the sum it's written this way. Let me be careful here. by pointing out that this sum is finite. So let me give you more generally, and maybe this will kind of deal with what I'm saying. If x is not equal to the empty set, then a typical element of is a finite sum of form. And this is true in general. I equals 1a of r sub I x sub alpha sub, where and I do the double index here to indicate the fact that x might be a very big set, it might be uncountable. But in this thing, you always have a finite sum. Even though you might have uncountably many things to do, you can only use finitely many of them at a time. Right? So for example, y'all remember how the direct sum was defined from groups? That's right. That's right. These are sort of vectors, so n1, n2, nk, where there exists n depending on element, such that n m is 0 for all m bigger than n. So it has to end in infinite string of zeros. Now, of course, in this direct sum, you have 1 0 0 0, you have 0 1 0 0 0, 0 0 1 0 0 0. So you have infinitely many things shifting to one forever that way, but you never have something that's infinitely long in the direct sum because everything is a finite sum of these things. By the way, let me give you another example. This is a Q vector space. Do I agree with that? Right, and again, these are sequences, if you will, of elements from Q that end in an infinite string of zeros. Right? Notice that you multiply the scalar all the way through. This is vector space. Can it, from your days in linear algebra, can you give me a basis for this? Everybody agree that's a basis. Because certainly, I think we would agree that this is linearly infinite, right? And since anything in here ends in an infinite string of zeros, you only need finite linear combinations to do everything, right? Notice, by the way, this vector space is countable not just in dimension, but in size, right? This is a, I mean, you can use the fact that countable, countable sets is countable. This is actually countable. And this, I like this example because it illustrates that Zorn's lemma is kind of a big deal. What about the correct product? Now you have no restriction, right? Would everybody agree this is a vector space over Q? You add two things like that, you get something like that, right? It's an abelian group. I think we'd have to agree. It's an abelian group. And the scale of multiplication is good, right? You just multiply, I don't know, some rational number Q by that. It's QQ1, QQ2. Give me a formula for a basis for this, and you guys can take the rest of the semester off. You can have a snow day every day. I hedge my bets well. You're not going to do this. I think that we would agree that 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, continuing, is a linearly independent set. Still works. But now you got a problem. Because not everything is a linear combination of this, right? This, the linear combinations of this cover everything that's in theory. But this is countable, and that thing's uncountable. So in a certain sense, most of the stuff in this new vector space can't be covered by the subspace. There's countably many things in this subspace generated by this, but uncountably many things in the whole thing. So what do you do for a basis? Well, I need something else, right? I need some. The problem is with linear combinations of this, I can never get anything that's ending in anything other than an infinite string of zeros, right? So maybe I throw in this new basis element, 1, 0, 1, 0, 1, 0, etc. Right? That actually should be linear work. But now, what's your next one? I mean, this is still a countable collection. So if you look at what's spanned by this, it's still countable. So there's got to be stuff left over. So maybe you throw in this one. This covers the odd ones, this covers the even ones. But now, and even back then, now there are definitely things that you can't throw in. Now you cannot add 1, 1, 1, 1. Because this plus this is this, and it's linearly dependent. So once you start making these choices as to what, you start eliminating things. This is why the axiom of choice in Zorn's lemma is so very important, because you're never going to be able to write this down. It's there. So anyway, that's probably a worthy excursion. But going back to the generating sort of bit, there can be infinitely many B's here, but as far as elements go, finding the elements, everything should be a finite linear combination over R of some things that you find in X. Okay. Any questions? Did y'all have y'all had algebra 1, didn't you, last semester? Here's one of the most embarrassing things about algebra. So we're 2 days into the second semester before I define what an algebra is. And that's what I'm now. Definition. Let's suppose that R is a commutative ring of identity. An R algebra I'll call A, algebra, is a ring notice I don't say that this ring is commutative. I will say it has an identity. It's a ring with identity. Equipped with a ring homomorphism. RA. With this is kind of a rule that I have. Those people that do commutative algebra at school, with the identity of if it's a ring homomorphism, it takes the identity of the first ring, again, the second ring. Such that f of r is contained in the center. A might not be commutative, but the image of R inside of A is commutative. It's contained in the center of the ring. Anybody want to, almost always when you see a definition like this, in mathematics, the way you build is you see somebody's cool example and you try to generalize this. Anybody tell me what this might be generalized? And this will give a kind of a good large example, I think, of algebras over a ring. Well, actually, that's right. I mean, if you have a commutative ring of identity and you look at its polynomial ring, this looks like it works, right? Polynomial rings are ring identity, and there's a ring homomorphism from R into here, right? And of course, Rx is commutative, so this is certainly true, right? So certainly that works. Can you give me a non-commutative example? Right, where the algebra is actually not commutative in general? I guess you could say polynomial on two non-commuting variables. But here's another one. Let R be commutative line, any one you like, and let A equal the n by n matrices over R. And my homomorphism where do you suppose this goes? It just goes to the diagonal R. And notice that the diagonal matrices is the center of M and R. Right? So that's exactly what you would hope it does. So that is an algebra. It's something that generalizes this. This is kind of one of the most important large examples of an algebra. Let me give you the following proposition, and then that'll be it. I'll probably let you prove this yourself. It's not too difficult. Proposition 6.1, I guess it is. If A is an R module, let me say this: R is a commutative ring of identity because I'm going to talk about algebras here. If A is an R algebra, then A is R module. Now, the trick is, so see if you can prove this, but how is the R module going to work? So I've got to define if R is an R and A is an A. I have to intelligently design what is a scalar R times A going to be? How am I going to do that? The problem is there's a tight mismatch. In fact, if you think about the matrix example here, R times a matrix needs sort of figure this out. How about this? We have this function F that takes my input and makes it go into A. How about this? So check that scalar multiplication turns A into an R module. It's clearly an abelian group because we already know it's a ring. Check that makes it an R module. Okay. Questions? All right. Well, welcome to your snow day. You all, if you don't have to travel, don't. Be careful out there, and I will see you on. Is today a weekday, man? I'll see you on Monday. Any questions out there? Anybody out there got questions? All right, I will see you all on Monday.